playing. Okay.
Me?
Please start the preview player.
We should.
Okay. All right. Now, I think we should be live. And now, as always, we need someone else to validate to observe us and to know that we actually
Witness
exist.
us.
Yeah. Yeah. There we go. People see us and hear us.
Yay.
All right. Well, we'll take a second. It's too bad you missed a really great conversation about. Actually, we may very get well back into it again, but
No, I'm spent. I'm sorry.
yeah, it's done. It's done. It's gone. There's no record. It's forgotten. It never happened. But that's okay. We will fill this hour with even more interesting stuff. So my guest today is Jason Wright. For those of you who don't know, AKA Astro Wright, a exoplanet researcher with Penn State. You were the advisor for Dr. Kimberly Cartier, right?
That's right. Yep.
Yeah.
She's a PhD, Penn State University, and I got to advise a lot of her projects. Although most of the work she did is actually with other people. It's pretty funny.
Is that, I don't know. Is that how it works with a?
It can. Some people really
PhD
want to.
Student? Yeah.
Well, some students really want to work with a particular advisor. They want to do what they do. They want to learn at their feet or whatever. But Kimberly really rolled her own. She was like, no, I'm going to go work with this person and this person and this person. And just, okay, you can be my advisor.
Right. But I'll let you give a more formal introduction here in a second. But I think just to give people some touchstones, you were involved in a lot of the observations of Tabby Star. You helped sort of get the word out there. You've been pretty.
My fault.
What's that?
That was my fault. That whole thing.
Was it really the whole the exo? Was it you who said, that could be a megastructure?
Yeah, I said that to Tabby in my office when she showed me the light curve. That's where it all started.
Oh no!
No, it worked out okay.
I totally did.
I just wish I'd been a little out in front of that one.
No, it's perfect. It's perfect. And that will be the part of the conversation that I think we have today. So what else? I mean, specifically, what are you working on?
I do a lot of things right now. Most of my time is spent as project scientist for a new planet finding instrument. NASA wanted to make sure that the United States had a great planet finding Doppler spectrograph to help out with the TESS satellite, which is going to find thousands of planets. And it finds those with the transit method, but just because a star gets a little dimmer doesn't mean a planet's going in front of it. You need to validate that. And one of the dominant ways, the primary ways that we do that is by measuring the Doppler, the radial velocity shift of the star to see if it's really a planet. Anyway, we at Penn State are building what we think will be the world's best Doppler spectrograph. And it's going to go on a telescope at the National Observatories at Kitt Peak. And so I'm project scientist.
So an Earth-based Doppler.
Ground-based Doppler measurement to do that follow-up. It's really exciting.
Before we go any further, this will give me a chance to get a question answered that I've had for a while. So the Doppler method for finding the radial velocity method, you're measuring how quickly the star is getting yanked back and forth by the gravity of the planet as it's orbiting around
the
it.
Star's motion and inferring that there must be a planet going around it, causing it to wobble, because stars don't just wobble around space all on their own.
The advantage, or I guess a lot of with TESS, for example, a lot of these planet finding instruments are using the transit method, where you're watching the light curve as the object is passing in front of the star.
Right. If you're lucky enough that the planet happens to have its orbit between you and the star, then you'll see the star get dimmer every time it goes around.
So does the radial velocity method give you a little more flexibility in case the planet is a little above or below the star? And where will it be better than, for example, the transit method?
Right. So the radial velocity method, it only can tell if the star is moving towards or away from you. So the planet has to, it's best if it's moving around right in front. But, if it's inclined a little, you'll still have a little bit of motion towards and away.
Right.
It's only if you get super unlucky and it's exactly in the plane of the sky that you won't see anything. So that means most planets will have some motion towards and away, which means in principle you're sensitive to most of the planets out there. Whereas the transit method, you generally only see, well, you only see them when their orbits are exactly perpendicular to the plane of the sky. The second thing is that you only get a transit for that brief moment when it passes in front of the star. So if the planet goes around the star every 5 years, then you got to stare for 5 years just to see one. And generally you want to see 3 to make sure it's real.
Yeah.
And so the transit method, you're most sensitive only to the planets that are right up next to their stars, the real scorchers that are generally extremely hot, unless that star is really tiny and dim. The radial velocity method, I mean, we are finding planets now with 10, 12, 15, even 20-year orbits, which you would never really find with transits. So there's a wider variety of planets you're sensitive to with radial velocities. On the other hand, a planet the size of Earth is very challenging to measure with the radial velocity method, whereas we can just kind of barely do it with space-based transit searches. And so it's a different parameter space. You can find the close-in planets, the tiny planets with transits, the bigger planets, the farther out planets with radial velocities, and that sweet spot where you get both at the same time, you can actually figure out what the planet's made of because you can measure its density.
Right. So you can sort of confirm with the two methods simultaneously.
When you get them both, that's when you really learn.
Yeah. But the number, like it's like 1% out there, right? Most of them are not.
I would say most of the planets we find, it depends on many of the planets we find transiting, especially the really obvious deep ones, we can usually get if you spend enough ground-based resources, radial velocities.
All right. So, and then when are we going to be able to do a better job of direct imaging? Isn't that sort of the holy grail, is moving to direct imaging of planets?
It's great when you can do actually take the picture. And, we have these amazing systems like HR 8799, where you can actually see the planets going around the star. In general, right now, when we do that, we're looking at young planets. And I mean, babies, like barely 1 billion years old, that kind of young planets. But when you have a big planet like Jupiter or more massive than Jupiter, when they form, they get really hot, and it takes them a long time to cool down, tens or hundreds of millions of years. And so when they're that hot, they shine in infrared light.
Right.
And a lot of these direct imaging instruments like GPI or Sphere they work at these infrared wavelengths. And so they can actually take a picture of these young hot planets. But if we were around another star trying to take a picture of the solar system planets, Jupiter is 5 billion years old. And so it's just too cool at this point. It doesn't shine brightly enough. And so you wouldn't be able to see them that way. You'd have to look at the planets in reflected light. And compared to the sun, the planets are really dim. So there is a hope the next generation of coronagraphs in space have a chance of doing direct imaging around the biggest planets, around the closest stars. And that's something we hope WFIRST will be really good at if it launches.
And the star shade.
The star shade is a really interesting idea of a way to do that. So when you got to suppress the light of the star, and you do that with these fancy coronagraphs, these fancy cameras that can get rid of the light of the star, but not the light of the planet. It'd be a lot easier if you could just, put your thumb up and block the starlight and see the planet next to that. But, the trick is if you're going to do that, you can't put your thumb up next to your eye. You got to hold it way out. And so the star shade is this idea that you just build this gigantic big thumb and you fly it out really far away from a space telescope and you line them up just right and block the star. When I first heard it, I thought it would never work, but I don't know. Maybe I'll make it work. NASA's amazing.
Yeah, it's funny. I remember the original proposal way back in the day. Like Webster Cache just sent out all of these crazy ideas, like a lunar elevator and a star shade. There's a bunch of these that were all part of the NASA Advanced Research Awards they were handing out. And this idea just keeps growing. And I just can't wait for someone to actually put such a machine out there.
Yeah, there's a lot of technical questions that are still out there about how feasible it is and the precision flying you have to do. And you're not going to be able to look at a lot of stars because that thing's going to take a long time to move.
Yeah, exactly.
So whether it makes sense is still not clear. But I agree. It's one of these out there ideas. Like, really?
Yeah.
Really?
Yeah.
Are you going to
that would work, yeah. And then match that up with some space-based interferometer mission.
I don't know, you need an interferometer then. I mean, people have talked about, you could use Webb. Just have James Webb Space Telescope
Yep.
look at it, or WFIRST look at it, or
Yeah.
That's the nice thing, is that the Starshade lets you build a general purpose telescope, and then when the Starshade's in the right position, you go, oh well, let's go look at that planet.
Yeah, yeah. All right, so exoplanets, and we can definitely take on some questions that people have about exoplanets. But the other thing that you are famous for, I mean, we talked about the megastructures originally, which is that your work on you just wrapped up a whole bunch of work with NASA's Technosignatures workshop. I did a video on that. There was a ton of really great information in there, and I think just like in general. Are we now at a place where we're allowed to say that searching for extraterrestrial civilizations is a scientific question?
I mean, I think we've always been allowed to say that. There's certainly people that will police what you're allowed to talk about with respect to extraterrestrial life. Someone made an interesting point. Someone on Twitter was telling me that back when people were working on Viking, there was a real associated with Martians and all this, sci-fi stuff. And so they were really careful because we're just looking for like fossils or maybe microbial life in the dust. And, they felt like they weren't allowed to if they said anything that was wrong, it would just be completely misinterpreted and they wouldn't be taken seriously as scientists. And I know that when Carl Sagan was doing Cosmos, that a lot of people thought it was really irresponsible of him to be talking about life in the universe and talking about the possibility of intelligent life elsewhere in the universe and communicating with them and SETI and all of this stuff. And or even ordinary stuff like looking for microbes on Mars. And today there's a different attitude. And I think a lot of that is that the Cosmos generation, we're in charge now. Like, we're the ones doing the research. And now NASA happily does a ton of astrobiology. Looking for life in the universe is one of its serious scientific priorities. And so I do think that's created a culture shift. Also, the discovery of exoplanets, so many of them.
Yeah.
It's now clear that these arguments that maybe Earth is unique or something, they
Right.
hold a lot less water. It's pretty clear that planets like Earth must be pretty common. We haven't found water on one of them yet, but it's hard to imagine none of them do.
Yeah.
And so that, makes the whole search for life more probable. And at that point, you're like, well, okay, so NASA can spend billions of dollars and it's totally cool to talk about life as long as it's stupid life. But as soon as you suggest it might have a brain, whoa.
Yeah.
And that contrast is becoming much clearer now. And so I was a little worried when I got into this 4 or 5 years ago that, people might not take it seriously and it might not be good for me. But for the most part, people have been very supportive.
Yeah, and you've done a bunch of research that we've looked at, one being the possibility that there were civilizations here in the solar system before us. Spoiler alert, none's been found so far. But this idea that we can and should be searching for some kind of intelligent civilization out there in the universe. For you, where does this come from? I mean, for me, I find, obviously we all were raised on science fiction. It told us to be expecting that we'd be jumping in our warp drive powered spaceships and heading off to visit these aliens. Where does this fascination for this topic come from for you?
It's funny because I think a lot of it came from just starting to get into it and realizing there's a lot of low-hanging fruit here. This discipline has been starved of resources for so long that it's clear there's just easy stuff that could have been done decades ago, but no one's funded to do it. No one's trained to do it. And
can you give me an example? Sorry, like what are some things that you think would have been easy to search for that no one's been able to do?
I recently taught a course here at Penn State called SETI, the Search for Extraterrestrial Intelligence. And now it's a regularly numbered graduate course. It's part of our astrobiology curriculum. And in the class, I did something that would be just impossible in any other discipline. I said, you've got to find an interesting research question that you can do for a final project in this class. and you have to make a significant contribution to the field, and that's your final project.
Yeah.
And in any other field, that's just ludicrous.
Yeah.
Because, there's all these hundreds of people who've been working on it for decades. Right. What could a grad student that just learned this possibly do?
Yeah. Find a new particle in the standard model. Yeah.
And I said, if you get it published, automatic retroactive A for the class. Doesn't matter how well you did. So we've already got one of those final projects published. Another one is going to get submitted next week.
Yeah.
And I was just in a conversation about a third one getting published. And so just simple stuff like, let's make a list of all the papers on SETI. Like, let's go look them up.
Right.
No one's ever done. Let's calculate, and we did this with Jill Tarter, whose idea it was. Let's just make a list of all the SETI searches that have ever been done. Publishable right there. Jill Tarter just used a lot of that data with a lot of work she's done and announced.
That's the thing they added to the SETI Institute website.
Technosearch, right.
Yeah.
So a bunch of that data
okay.
was part of the final project. Like they went through and hunted the literature and that's why Penn State had an involvement in that. How much searching have we done? How much of the cosmic haystack have we actually searched? And you look and it's like people have done these rough order of magnitudes, but no one had ever actually calculated it. So we just calculated it, published right there. So, I mean, just basic stuff like how much searching has happened. Let's make a list, like stuff that, normally would be in a textbook or something like that. No one's ever had the time to work out. So anyway, I've got a long list of projects that we can just, rattle off and do them in a semester or something like that.
And so if you want an easy A, there you go.
Well, an easy published paper.
Yeah, an easy published paper. You could jump ahead that many researchers work on for years. Boom, just get a paper. Just keep publishing. So, publish or perish. So one of the things that attracts me to it is that no one's working on it, and it's not that hard to make a lot of progress. So I did my PhD in exoplanets, which is a really hot field, and so it was very competitive. And, it was like, got to hurry up and get that paper published because we're worried that the other groups are going to publish it up from under us. And I mean, it was stressful. And so I've worked in that mode. But I'd much prefer to work in the mode where not everybody's trying to solve the same thing. Because if you're in a hyper competitive field, it's great when you win and you have the advantage and you get that paper out first and it's better than everyone else's. But, if you weren't in there, if you weren't in that scrum, if you weren't among that, one of the examples I like to give is if you ever watch like 6-year-olds play soccer or something like that, right? There's like the ball and everyone wants to be at the ball and they're not playing the cool soccer. All the kids are all around the ball and they just follow the ball all over the field and everything, right? Yeah.
And it's like, it's good that you're trying to kick the ball, but if you weren't in that big mob, someone else would be kicking it. And it's okay. Like science would not suffer if you weren't working on that particular problem. Whereas there are a lot of things like SETI where there's a lot of work to be done. And if you don't do it, no one's going to do it.
And the irony is, like, it is the most important question that a human being can ask. Like, I think it is up there. Like, if you had 2 envelopes and you went to any scientist and you said, in this one envelope is the answer to the question of whether or not we're alone in the universe. And in this other envelope is the question of, like, is it possible to make a computer that down to 8 nanometers or some other unsolved technical challenge or question. I would assume that most scientists would want to know the answer to that scientific question about whether or not we're alone in the universe. Like it feels like one of the most profound questions, absolutely scientific, right?
Right, absolutely.
Yeah. And yet there is this desert of research in this field.
It is interesting the way that just sociology plays into what we think the interesting questions are. I mean, we often think about scientific progress from, the ancient Greeks to the, Galileo, and now we have iPhones. Like it's all this natural progression. But really, like the questions we think about working on are really determined by just what people say a good problem is. And you see lots of people working on something. It doesn't seem like anyone's making progress for so long. And then these big questions like SETI are sitting there, just, someone should go work on that.
Yeah.
So it's funny. Someone asked me in the SETI class why I work on it and if I really think we're going to find anything. And I admitted that, if I lived in an alternate reality where NASA was totally gung-ho on intelligent life in the universe, And all of these astrobiology institutes was all about finding technosignatures. And if you said, well, maybe there's microbes on Mars, and you got laughed at and you couldn't get any funding, then this conversation might be about me saying, there could be fossils on Mars. We should really be working on this.
Someone should check.
This is who I am. I want to, this is low-hanging fruit, and it's a big question, and no one else is here. And look, come join me. This is great.
Yeah. All right, so let's talk about technosignatures. Now, everyone is very familiar with this idea of radio transmissions, that you're going to, turn your big dish to space and you're going to hear the radio transmissions.
Right. You'll have the headphones. You'll be able to
That's right. Yeah, you'll sit out there and you'll listen, right? Like Jill Tarter did. But that is well, yeah, no, I know, but it was based on Jill Tarter, right? But that is that is still the gold standard, isn't it? Like it's like there's a reason why so much energy has been put into that.
Well, again, I think this is sociological. I think Sagan and Zemeckis deserve a lot of credit for putting this very tangible, easy to imagine thing out there. Like, we understand you want to communicate at distances, you use radio waves, right? That's how you do it. And so it makes a lot of sense. But the other kinds of SETI that are out there are just as old and no less credible. I mean, there's a lot to be said for using laser pulses or continuous wave lasers. The paper on that came out 4 years after the paper on radio SETI. And Freeman Dyson saying, hey, we should look for inevitable consequences of industry. We should look for waste heat. That was the year after the first radio SETI paper. So, these ideas are just as old. And it's an interesting accident of who was involved and what their background was, that the canonical image in everyone's mind turned out to be that in radio SETI. And it's certainly where most of the work has been done. But I don't think it's because it's the most credible form. There's a lot to be said for radio SETI. It's a really strong argument. And if I had a radio background, it's probably the kind of SETI I would do. But I don't have a radio background. I have a background in other things. And so I apply my strengths and my talents to the problem.
But there are, I guess the point is that there are unambiguous signals. Like there is, if you're able to receive a signal in the radio spectrum at the right place, it can only be coming from an intelligent civilization. There is no natural phenomenon that could generate that. And so we have radio dishes. And I guess, this segues into what my next question is. Of the methods that we could be searching for technosignatures, which is the one that you think is the coolest, gives the biggest chance?
Oh, well, that's a totally different question.
I'll give you sort of like, from my perspective, like things like searching for evidence of type 3 civilizations, civilizations that have rearranged the entire star structure of their galaxy and enclosed them all in Dyson spheres, so you can see the infrared infrared radiation coming from that in a funny shape. That just tells you a whole bunch of things all at the same time. And so it's this really, and it's a surprisingly straightforward thing that you could look for out in the universe. So it fulfills a whole bunch of things all at the same time for me.
Yeah.
That's what I'm getting at.
We don't know what technosignature will be the first one that we identify that lets us say, that's it, that's them. And so one of the things we did in that report, we had a lot of conversations before we wrote the report about, what's a good technosignature? What makes a technosignature good? And a Penn State graduate student there, Sophia Sheikh, put them all together and sort of listed the 9 qualities that you'd really like to have in a technosignature. And one of the important ones is what you were just articulating, the ambiguity. Like you see something and you're like, okay, that's interesting, but, is it aliens? And so with something like Tabby's star, with these very strange dips, there was nothing about that said this must be alien technology.
Right.
It was weird and it's suggestive. And after 2 years of intense study, still not knowing what it was, that's a big enough anomaly that we should start, suggesting that we should look into that possibility. But it's ambiguous. Whereas, you pick up I Love Lucy, there's no way that's natural, right?
Right.
Nature accidentally create Lucille Ball, right? Doing her show or whatever. So the nice thing about radio communication SETI or laser communication SETI is that it really is unambiguous. There's no natural phenomenon that would do it. So when you see that, you're done. You win, front page New York Times, you've got it. There is alien life in the universe. But the trade-off for most of those is that you're not sure that they're going to do that. Why would they necessarily use radio waves? And there's a lot of reasons why they might, but there's also a lot of reasons why they might not.
Sure.
Why would they use lasers? Why would they be trying to get your attention? Why would they communicate like that? Whereas something like waste heat, why would they use energy? Oh, well, because life uses energy. That's what technology does. It manipulates energy. So looking for the waste heat of industry, which is an inevitable byproduct of energy use, is much more inevitable. But just because you see some heat, that doesn't mean it's alien. So there's this balance between inevitability and ambiguity. And different people live in different spots. Some people go, they want to win with that one observation, and others are willing to say, well, let's go look for the anomalies and hunt them down. The nice thing about that route is that if you find something really strange and you study it and it turns out not to be aliens, you still win.
Right.
You found something really interesting.
Strange, yeah.
Strange before. And so going anomaly hunting has a lot of direct side benefits in astrophysics.
It's all right. So we got a bunch of questions came from the audience. So Karux asks, is the problem with technosignatures the getting funding problem mostly, or do we need better measuring devices first?
Oh, funding is the problem. It's the
problem.
It is the problem. I mean, we have these amazing multi-purpose observatories, right? The Hubble Space Telescope, James Webb is going to launch. Something like the Large Synoptic Survey Telescope is an incredible general purpose instrument. We are swimming in data. And, before we start talking about better measurement devices for SETI, let's dig through the decades of data we've already collected and start there before we start saying, we need some more data.
Right.
Definitely.
I mean, you mentioned like the square kilometer array in the paper would be capable of detecting leaked radio emissions from within dozens of light years of Earth.
It's a real watershed for the field, I think. And Chaz Beichman at the workshop really hammered this home. He's saying we're at the point where we could actually detect ourselves around the nearest star. And that's new. That's never, we haven't been there before. We're at that threshold. It really feels like if we can detect ourselves at interstellar distances, you don't have to imagine much, louder civilization. That now you're leaving. Well, why would they try to get our attention? You're like, they wouldn't. We're just seeing what civilizations do. Yeah.
Neil Yu is asking, do you have any thoughts on the ELT? I think that's the EXO Life Telescope. Have you been involved?
Extremely large telescope.
Not the EELT.
Not the EELT.
Not the EELT. Oh, I think are you talking about the EXO Life Finder or let's talk about both because they're both pretty cool. I don't know if you probably know the extremely large telescope, the 39-meter telescope that the ESO is working on.
Right. Yeah. One of the three, one of the three next generation 30-meter class telescopes with the Giant Magellan and the 30-meter telescope. All three of those are going to be really, it's hard to articulate. What I love about instruments like that is we don't know what they're going to find. I remember reading a report on the 30-meter telescope talking about how it would find, 30th magnitude objects in this stuff. And there was a footnote that said the existence of galaxies this faint is actually completely hypothetical. We don't know. We don't know how many we're going to see.
Right. The point is we'll see them all.
I love that we're building these instruments into parameter space and just saying, we don't know what we're going to see. We'll see something. It'll be amazing. And so because of that, we know they're going to be useful for something like SETI because they're just going to generate so much data and find all these great new anomalies.
Yeah. I think he was talking about the EXO Life Finder. I don't know if you've seen this instrument at all. It looks like a ring with a bunch of 9-meter telescopes arranged in an array of like 25. They should be able to image. It was done as a Kickstarter to be able to get the initial study done, and in theory, it should be able to image continents on
ELF.
The ELF. So
right. Yes. I don't know enough about. There's some interesting technical miracle going on here with this particular telescope that I don't understand. I'm not an instrument person,
right?
But there's some technical feat that's being proposed here that lets you do amazing stuff.
Collapse the wave front or something.
I don't remember. Anyway, it sounds great, of course.
Yeah. Would you like images of continents on other planets? Yes,
course.
please.
And it sounds too good to be true. I guess I think we're going to find life with this thing is a hard sell because people aren't going to believe you. First of all, like, how do you know you're going to find life? And I think for something that big, I mean, with that level of resolution, there's so many applications for it. And that's why I really like things like the ELT and the TMT and the GMT, that everyone wants to use this telescope for all kinds of astronomy and astrophysics. And part of, we quote this, I think it's for the first time published in that Technosignatures report, Freeman Dyson's first law of SETI investigations, which is that you need to have interesting science even if you don't find alien life.
Right.
And so I'm all about the general purpose instrument that we can appropriate for so many purposes, and that even if at the end of a career we still haven't found anything, we've still found a lot.
So Vovacat17 asked, what if we do open that envelope and find out that we are alone in the universe? What are the implications does that have? Do you...
Well, a null result is, proving a negative is really hard, right? I mean, when do you say...
But I gave you the envelope. It told you the answer.
Oh well, this is a weird counterfactual. All right. I mean, what do you mean alone? I mean, do you mean that there's no life in the universe? Or
there's no either one. But let's say there's no life of any sort in the entire, no complex, no simple, no intelligent life anywhere in the entire universe.
Man,
in the Hubble sphere.
That's kind of scary to think about how unique. I mean, for me, the existential weight of knowing that the only life in the universe just happens to be on this planet. I don't know. I mean, it makes thinking about all the species dying off right now, real. I mean, the fragility of the biosphere. And I know, the biosphere has survived for billions of years against asteroid impacts and snowball Earth and all the other stuff. And so it's pretty resilient. I mean, life will probably persist for a while, but knowing that it'll go away when the sun evolves to a giant phase, knowing that we really could mess it up and just end it all, with a push of a button, that for me, it just amplifies how important it is to take care of what we have and to do something to make sure that it perseveres. Because man, what did someone say? That if we're all there is, it's an awfully waste of
it's a big waste of space. Yeah. And it puts the pressure, right? It puts the pressure right directly on us and says, get it together, because you're all or at least, dolphins or octopuses, like it's on you or whatever.
I do worry that on the flip side, that if we find alien life out there, that it'll be like, oh, there's nothing special about Earth. We can mess it up. We're just this puny little primitive thing in the corner. And, it doesn't matter if we go away. And so I think the flip side, if we're alone, then man, we have a really special obligation. We already do. I mean, I think we already have that obligation, but it really drives it home.
That's my default view, is I'm just going to assume the worst. And that
act as though this is it.
Act as though this is it, exactly. And so, anything that we do find is a bonus, but otherwise, we need to take care of our planet, and we need to figure this out. And then if the aliens are like, "Don't worry, we got this," then we're like, "Oh, great!" But until then, we need to not mess this up and not get lazy about it.
I just say it also, I mean, when we think about the long run future of life on Earth, I won't say humanity, because, give us a billion years, I don't think we'll qualify as humanity anymore for whatever reason. But when we think about the long run, if the galaxy is filled with intelligent life, then our future is tied up with theirs in complicated ways that we can't even guess at. But if we're the first, then it really is our future out there. And we need to think about what that means as we're on the cusp of realizing it.
Yeah. All right. So there was another question here. Crush Not asked, I lost it. Hold on. Wait for it. Oh, I lost it now. Oh, there it is. So what other astronomical targets can our radial velocity telescopes target outside the exoplanet hunt? So can you see some uses of the radial velocity method for other things as well?
Well, the radial velocity method was invented to study stars. And a lot of us that do this, we like to joke, we're really, really precise stellar astrophysicists. We study the stars super well. And when we try to measure the stars' motion, sometimes there's this noise, they keep wobbling around. And so we have to subtract off that planet so that we can see good stuff, which is stellar atmospheres. I mean, I've taught courses in stellar atmospheres. I haven't, taught a formal course in exoplanets before. So yeah, we study stars, we study how they pulsate, we study how their atmospheres move, we study the stars that orbit stars. The coolest application of the radial velocity method, which is still unrealized, it's really hard, I'm not sure it's really going to work, but the coolest one is to not look at stars, but to look at distant quasars. So these, are black holes at the edge of the universe that are swallowing stars, and they're spewing out these jets, and you get this really bright light that you can see for billions of light years. And along the way, it passes through clouds of gas. And when it passes through a cloud of hydrogen, the hydrogen absorbs its wavelength. But because the universe is expanding, every cloud of gas along the way absorbs a different wavelength. And so you end up with what's called the Lyman alpha forest, which is just this pattern of missing colors of light in the quasar spectrum. And so what you're seeing is every cloud between you and that quasar in the whole universe. Now, the universe is expanding, which means that the velocity between you and those clouds is changing. Actually, it's not just because it's expanding that it's changing. It's because of the slowdown, the acceleration of the universe, and deceleration depending on what epoch you're in. The radial velocity method lets you see that change in velocity. You can see the cloud changing its velocity with respect to the Earth because of the acceleration of the universe. It's a direct measurement of that. And it blows my mind that that's even possible, that they're even talking about that.
Yeah.
But they are building instruments. They're thinking about them anyway. So there's an instrument Codex. It's a very large telescope that's being designed to do this. And that it blows my mind.
Yeah.
We can measure the expansion of the universe directly, see stuff change.
Right. And this is important because there are really two calculations, two very accurate measurements for the expansion rate of the universe. One from the speed that distant galaxies are moving away from us, and one from the cosmic microwave background radiation. Both have fairly precise error bars, and both disagree with each other.
A little bit. They disagree a little bit, but we're at the point where we think it might be significant. Yeah. I hope this can answer. It'd be very cool if radial velocities could. But one thing to keep in mind, I don't know, I haven't studied this. I shouldn't weigh in too much with any authority. But there's a big difference between measuring something and measuring it precisely enough to distinguish between models. And so just measuring that the universe is accelerating or decelerating isn't news. It's a technical accomplishment, but we knew that. The question is it accelerating this much or is it accelerating that much? And that's a whole other level of difficulty.
And I don't know if you saw, like, just a couple of weeks ago, really interesting new technique for potentially using quasars as standard candles, that it looks like the force of dark energy might be changing slightly in the early universe.
Well, that would explain, as I understand it, that would probably explain
it
this.
Wouldn't fully. It would partly. But that's probably the way this is going to happen. Is you're going to explain the discrepancy in tiny little bits until the whole thing has been solved.
Yeah.
Some more questions here. So Felix Peterson asks, how much can private individuals actually help, and how is running SETI at home on BOINC useful at all, for example? And Peter Yannick asks kind of the same question. So what do you think about SETI at home?
Oh, SETI at home is great. SETI at home is amazing. I mean, I think a lot of people don't realize that a lot of distributed computing that people use for, Bitcoin mining and protein folding. I mean, a lot of it started with Dave Anderson and the crew at Berkeley with BOINC and just, figuring out how to harness everybody's computers for SETI at home. So SETI at home is still going strong. It's still really valuable. And the reason is that when the radio SETI experiments go on, they collect enormous amounts of data. So to give you a sense of scale, when we looked at Tabby Star with the Green Bank telescope, I had, I don't remember, 12 hours or something like that of time on it. In that less than one day that we were on the telescope, with all of, we used new mode no one's ever commissioned before, we collected 610 terabytes of data. 610 terabytes of data under a day with this equipment. We had so much data that when I talked to the Penn State folks, I'm like, can we store it at Penn State? They're like, sure. And I'm like, all right, I've got the data. I need it. They're like, wait. we don't have that much today. We're putting it online. And as fast as they could put the drives online on this new supercomputer, we were uploading it. And so we thought about driving it all up on trucks because, a truck, because that amount of data.
Fastest way to send data.
And they were like, we can't handle it. Just dribble it over the internet. Just use a secure copy command, because that's only as fast as we can put stuff online. That's a little exaggeration.
Right.
Huge amounts of data. Now, I mean, to analyze all of that is basically impossible. I mean, it's possible, but the resources required are outrageous. So what they do is they make some assumptions about the sort of signal that they're looking for, and they quickly analyze it for that, and then they save the rest onto disk with a huge data compression. So they don't save the raw files, the raw voltages that come down from the telescope. They save it in what are called waterfall plots in certain ways. The cool thing about SETI at home is that it harnesses your computer processor at home to do a lot of the stuff we wish we could do with all of the radio data. And so it makes the searches much more powerful because it lets them look for many more kinds of signals than they can otherwise. And so that's a great way to help. It just runs in the background. All you got to do is pay a slightly higher electricity bill, but it warms your house while you're at it. So it's no big deal.
Right. Better than mining cryptocurrency.
Yeah, right. In winter, it doesn't cost you a dime because thermostats. So yeah, those are great things to do. And Zooniverse, everything on Zooniverse is great. Go to Zooniverse, go to Planet Hunters, go do all of that stuff. It really helps.
Yeah, and it really kind of feels like today being a big database programmer is one of the most useful skills for being an astronomer. When you look at, there was a new release of data that just came out. It was like something like 18 petabytes or something. It's like a new version of the Sloan Digital Sky Survey. I forget the group that released it, but a down to 20th magnitude image of every part of the entire sky or something just ridiculous that you can then grind through to find asteroids and supernova and all that. And so that's my recommendation. Everyone knows it says how can I get a career as an astronomer? My recommendation is
programming.
Be a computer programmer. Yeah. And
when undergraduates ask me, how can I, do research? What are you looking for in an undergraduate researcher? I say, can you code?
Yeah.
Because I need you to write some programs, simple programs. You gotta know how to code.
And the worst case scenario, if that whole astronomy thing doesn't pan out, then you can just get a job at Google or Amazon for $300,000. So
yeah, exactly. And I mean, I mentioned Zooniverse, but I should give it another shout out. It's an amazing resource where anyone who wants to help out with astronomy or lots of other things can actually put the human mind to where it's needed for all these projects. And of course, your viewers probably know this, but it was Zooniverse Planet Hunter citizen scientists that spotted Tabby's star first.
Yep.
And said, isn't this weird? And then it was citizen scientists that contributed to the Kickstarter that Tabby put together to actually solve the whole thing. And it worked. We figured out that we haven't solved the puzzle, but we do know it's dust now. And that's thanks to all the citizen scientists that helped with the Kickstarter. So yeah, there's a big role for the public to play.
So Zerore asks, why are GoFundMe or Kickstarters used to supplement your funding more often? I guess it's why aren't they? Tabby Star demonstrated that there is a public interest in helping to support science directly. Now, obviously, it is like the charismatic megafauna of exoplanet research, but with this most important question that could possibly be asked with SETI, can you see a more direct involvement? I mean, the SETI Institute is privately funded, but can you see, I'm answering my own question here, but can you see a more direct involvement from the public in helping to get to the bottom of some of these questions?
I can, but like you mentioned, it's gotta, in order for people to feel like they are contributing to something, they want to know what it is and they have to have heard about it. And the truth is, most really important research, it's not grabbing the public eye and people won't know why it's so important to fund. So it's great. It's great when something like Tabby Star grabs the public attention. It gives us an opportunity to talk about our research, to explain the science to the public. It's a great hook for all sorts of interesting science and outreach. And in those cases, it's very appropriate for us to say, hey, help us do this. We want to do this quickly. This is not something we can get funding for right away. And I think Tabby did a really good job of rewarding the backers, staying transparent about the data, and making sure they felt involved and understood and could see the tangible results of their contribution. But that is not a viable funding model for most really important science. And so the one of the most valuable things that people can do, and it sounds boring because it's disconnected from the science, but is, make sure that the National Science Foundation is a high funding priority for Congress, and make sure that Congress stops deciding what can be funded and what not, and let peer review happen, and support that kind of basic infrastructure so that things you didn't even know were happening that scientists said were important, like Kepler before it was Kepler, and planet hunters and stuff can all happen in the first place, and then people can get involved and see the payoff.
I think you're wrong.
Oh,
yeah. I mean, I think you're right, but I also think that demonstrated, and I have seen enough of the enthusiasm for this kind of work that there would be. I'll bet you there could be fairly large foundations raised from the public to help fund things like Sloan, for example. Like, there are these private foundations, but I can see things being kickstarted and fundraised by larger groups of people. My worry with that is that it would go preferentially to the kinds of things that have a lot of sort of showmanship, as opposed to some of the grinding science as you dig through the Lyman alpha forest. You know what I mean? Like, I think that would be the
so risk. You think there's a big appetite for kickstarted science?
I do, yeah.
Isn't already happening, and that if more science kickstarters were out there, more of them would get funded.
Yeah.
That's interesting. Maybe we should try more of them. That would be great.
I'd be glad to partner up. If you want, if you have some research project that you want to try and get some money for, and you want a showman to help you try and raise some awareness, I'd be glad to put my money where my mouth is.
You have baited me, and now I'm going to take over your show.
Yeah.
And I'm going to make my pitch.
And we'll figure this out.
We're going to figure this out. So,
yeah.
So the big one, obviously, Search for Extraterrestrial Intelligence is not funded by NASA. It's not funded by the National Science Foundation. And we're trying to change that. That's part of what the Technosignatures workshop was all about. But, even if NASA funds it, nothing says that a senator, just like happened in 93 and before that in 1990, isn't going to stand up and grandstand about wasting money and just cancel the whole endeavor. So it needs to be permanently funded. And so Penn State has committed to making this happen in a permanent way. And so we've started the Penn State Center. This Penn State Extraterrestrial Intelligence Center. And the idea is to create an actual endowment where we will do this in perpetuity, so that when I have a student, like I do now, a graduate student that wants to get a PhD in the field, they don't have to worry every summer about how they're going to fund their research. Yeah. They don't have to be a teaching assistant every single semester. They don't have to write a paper and then say, oh, right, but how am I going to pay the author charges to get this published? They, go to an astrobiology conference and say, gosh, who's going to pay my plane flight? These are the sorts of things that just always happen in funded research.
Yep.
And that it's one of the reasons there have only been 5 PhDs in SETI ever, anywhere. Only 5 people have ever pulled it off. And 4 of them work for Paul Horowitz at Harvard, and the other is Andrew Siemian at Berkeley. So if people, we're gonna get more into this, and I don't have like a GoFundMe button or anything like that, but I will. Yeah. I will. And that is how people can help. And I promise we will do more cool science like we keep doing, and we will publish it, and we will thank our donors.
Yeah. And whenever you need help getting the word out, let me know.
I will. I am letting you know, and I will continue to do so.
Let's see. I had some other questions there. Hit me with more questions, people. Let's see. So, Space TV asks, what do you think is the most interesting mystery in the universe? If you had unlimited funding and you could target some big mystery, what would you want to go after?
I find fundamental physics just amazing, like the nature of matter and the nature of the forces. And, we still struggle with issues like, is the universe deterministic? Like, is quantum mechanics deterministic? No, I'm not really totally sure yet. Like, it just boggles my mind that quantum field theory is this fantastically successful theory that we can use to explain every observation that we've ever made, but we can't answer basic questions like why does the wave function collapse? It's amazing to me. So that's the stuff I find the most interesting. And I guess, you know, it would have been cool to go into that field. On the other hand, lots of really smart people are there. Lots of smart people are following that soccer ball around the field. I don't like to think I could make a big contribution.
And it really feels like a lot of them, they've hit a brick wall. I mean, that's sort of one of the terrifying things about.
I think there's a lot of interesting developments that have happened in the last couple of decades, but they tend to be the people doing the stuff that not everyone else is chasing. So like string theory seemed like really promising for a while, and people complain about, you know, the LHC didn't find anything new. But I think there's stuff going on. But again, it's following the soccer ball. There's a lot of low-hanging fruit in areas that aren't well funded.
Yeah, but the great disappointment of the Large Hadron Collider is that it filled out the standard model of physics and hasn't been able to figure out anything beyond that.
Right. So to be clear, the LHC is a fantastically successful instrument, and there's a lot more to physics than finding new particles and driving the yes but why one level deeper. And so I think in some of the LHC failed is completely overblown. It's been a fantastically successful instrument, but right, there were no sparticles, right? There were no Stau particles flying out of it or like that, and so it was oversold in the fundamental physics angle, perhaps. In retrospect, certainly. Of course, it had found them, then it'd be a different story.
Let's see. Hit us with some more questions if you want. See. So Mike McHugh asks, is it better to look for laser-like communication than radio? So do you have a preference between radio or optical SETI?
Well, I'm an optical astronomer, so I have a completely objective and unbiased view on this now. There are strong arguments for both. I've been involved in both. This is a game where we just don't know how it's going to work, and we can't. I mean, it's fine to say this is where I'm going to put my efforts. This is where my personal bias say things are probably most likely, but it's really important not to say, and therefore their work over there is no good, right? We don't know where it's going to come from, and it makes sense to distribute our resources among lots of different things to check. And so as an optical astronomer, I like the optical stuff. I like going after astrophysical anomalies, but that's also because my predilection is to go find interesting puzzles to solve. So I think, Tabby Star was a fantastic mystery, and I'm still really intrigued by it, even though it turned out to be just dust of some really interesting variety. So for me, it's the anomalies and optical stuff. Between lasers and radio, no, I don't have a preference there. I mean, two of the most interesting things that are happening are Breakthrough Listen, who's going to, they're going to do stuff with Meerkat on these gigantic microwave surveys of huge swaths of sky. But then you have Shelley Wright at UC San Diego, who's got PanoSETI, which is going to search huge swaths of sky for radio. And they're both just really exciting. And no, I can't pick. Sorry.
There was a good one here. Yeah. So Kurux asks, is there any work going into deep learning for processing the science measurement date, the effort in private corporations to measure people as astronomical? So all of this energy into AI, deep learning, being applied to the work that you're doing.
Yeah, absolutely. So, I mean, the Breakthrough Listen folks just had a press release a while back about machine learning and how they'd trained a computer to find fast radio burst signals in their radio data that they were using for alien radio signals. And so that's a great example. One that I'm really interested in is these classifiers, because we have way more data than we can look through, even with something like Zooniverse, even with all these people looking at things. Because, we have to say you're looking for X, and then if Y happens and it's not what we were expecting, even people might miss it because it's not what we asked them to look for. So it'd be great to train these classifiers to say, oh, okay, that's a galaxy, that's an RR-Lyra star, that's a transiting planet, that's a heartbeat star. I don't know what that is. And it's that last part that's very tricky, because we know how to train classifiers to find the expected. The question is, can we train them to find the unexpected? Because right now you train something to separate cat pictures from dog pictures on the internet, right? And it's great. It's like dog, cat, but then you give it a picture of the Eiffel Tower and it's like 75% dog, 25% cat, right? And he's like, no.
Yeah.
It should be 0% and 0% and 100%. I don't know what that is. And that's the tricky part. If we could get them to do that, then I think we could do a lot of great stuff.
You can pass this one if you want, but Norwegianization asks, does the UFO phenomenon fascinate Dr. Wright? So how do you, I mean...
Yes, it fascinates me, but not for the reason it fascinates ufologists or ufologists, or I don't know how to say it.
Yeah, I think ufologists. Yeah, yeah.
It is really interesting, but I don't think it's interesting because it's likely that there are lots of phenomena in the sky indicative of alien technology that astronomers have all collectively missed somehow.
Yeah. Yeah, but it is like, clearly, I mean, I think that is part of the problem, why it has a bit of a stigma, is that there's been a lot of people asserting aliens without evidence.
So the touchstone for me when approaching SETI is, and it's much criticized, but it's true, Carl Sagan's extraordinary claims, extraordinary evidence. And what that practically means, if you're coming into this field, is that, well, of course you entertain the hypothesis. The reason we're doing this is we want to find alien life. But you have to take a scientist's skepticism to that. And you know that because you really want to find it and you want to be right, you have to be extra skeptical, even more skeptical than peers who aren't working on it. Because, as Richard Feynman said, the number one rule in science is not to fool yourself, and you are the easiest person for you to fool.
Yeah, yeah.
So I don't think there's anything wrong in principle with thinking about UFOs and all of that stuff, as long as you're going in with an extreme skepticism and an extreme bias towards this probably isn't that. And if someone goes in with that and studies the phenomenon in that context, then that's great, because I think it's an interesting phenomenon. But if you're going in because you want to believe, as they say, that's not, I think, a scientific attitude. Now, oh dear, oh sorry. Anyway, I should caveat all this.
My daughter gave me that as a Christmas present. I think it's great.
Caveat all this. I do not know very much about
well, no. So
I'm not speaking with any expertise.
No, and I don't
bias as a scientist in general.
I don't have any either, right? I mean, for me, I always say to people that the question of whether we're alone in the universe is the most fun. As I mentioned before, it's one of the most fundamental questions that we can possibly ask. The ramifications of that are enormous, and so if we say that this thing is true, I want to know for sure. And so I want the best evidence. I don't, if your evidence is, a person who saw a thing, that is not good enough evidence for me. I want to be able to hop in the starship. I want to be able to, put the strange metal in front of a mass spectrometer, and I want to know beyond a shadow of a doubt that this evidence that you're claiming is true. And until then, I remain utterly unconvinced by the evidence that you're putting forward.
I think Tabby Star is a good example of this. That the hypothesis, that this looks consistent with megastructures and stuff, that took years. I mean, Tabby, who's an amazing stellar astrophysicist, worked for 2 years and could not crack the nut, and that says a lot about how hard this puzzle really is to figure out. And so after 2 years of working really hard to figure this out and not really having a good explanation, we made a list. And I did this, Kimberly and I had a Scientific American article where we listed everything it could be, and all the ideas, as I like to say, they're all bad ideas. None of them really. They've all got big problems, but they're the best we got. And of those, I don't remember, 10 ideas or something like that. One of them was this megastructure thing. And then we worked really hard to study it, and we showed that that wasn't it. And so that whole thing was not a, oh my gosh, maybe it's alien. Long slog of constant skepticism. The explanation of last resort kind of popped up as one of 10 and then got put to bed.
Yeah.
And so if that's the attitude, then okay.
Yeah. Yeah. So Just and for me, like I find I generally have these conversations with people on my channel because they're like, Fraser, do you believe in UFOs? And I'm just like, and if they believe in UFOs and I clearly don't, it's just that I'm asking for more evidence, and me and this person may have different qualifiers for how much evidence. But as you said, extraordinary claims require extraordinary evidence. You cannot just assert this thing exists, and you definitely can't say what you think that it is. You have to be able to prove that it is what you is. And until then, it's just a UFO. It's unidentified, it's flying, and it's an object. And if we knew what it was, and if we knew it was aliens, then it would be an IFO. But until then, right? They're just unidentified, and you don't know what it is, and it's probably Venus. Like 99% of the time, it's probably Venus. But,
okay. Well, like I said, I don't know very much about it. But yeah.
Well, I mean, it's just like it's just another. I mean, for the most part, it is another conspiracy theory, right? So just add it to the bucket of the conspiracy theories out there that people are saying that they see a thing, and that thing is being covered up by the powers that be. And
so the one thing, okay, so here I can speak with some authority as someone who has, held NASA grants and executed NASA grants, as someone who's been at the telescope, as someone who works in this field and everything. And Jill Tarter, I think, put it best. Like, if we found something, would the government shut us up? Would they somehow suppress it and make sure, for whatever reason? And Jill says, we wish the government paid that much attention to us. Oh my gosh.
Yeah.
That would be great if they thought what we were doing was important enough.
Yeah.
Because then maybe they'd fund us.
Yeah, maybe they would fund you. Yeah, but they don't. They don't care.
No, scientists are terrible at keeping secrets. And we're really bad at being told what to do by bureaucrats and people.
Yeah. Yeah, absolutely.
And so, no, there is no way astronomers know about aliens and are somehow being silenced. It's just not the way we work.
Yeah, absolutely. All right. Well, on that note, where can people find out what you're working on right now and follow you?
Twitter is where I do most of that sort of live stream of consciousness stuff about my science. So it's astro_Wright, WRIGHT. And when I have something longer to say than 280 characters, I usually put a little more thought into it and put it on my blog, which you can get from the Twitter handle or feed, or just fine.
And you jumped into the whole how much popularizing of Oumuamua and other things should other perhaps prominent scientists be doing or not doing. And I thought you had a great, very even-tempered, balanced response. So I highly recommend you check out his blog. Just search for Astro Wright. Wright like his last name. And what is the research that you're working on right now, if you can talk about it?
Oh, well, it's primarily this great radial velocity spectrograph that we're building for NOAA at Kitt Peak. That's going to find, it's going to be a great instrument, and we're going to find lots of planets. Hopefully, we're going to find Earth-like planets around sun-like stars. I know that's a thing that people keep saying we find.
Keep waiting for Earth 2.0.
Right. It's hard to summarize why it's different than all the previous ones, but this will be one of the most, if not the most precise radial velocity spectrographs on the planet. And it will be open to the whole U.S., the whole world community to use through NOAA's amazing open skies policy.
That's awesome. All right. Well, Dr. Wright, thank you so much for taking the time to chat with us today. And let me know when you need help promoting your endowment for SETI researchers. I'm on board. I'll help out.
On the list.
No problem. That sounds great, man. All right. Thanks a lot. Thanks everyone for watching. Thanks for the moderators. Thanks for all the questioners. And I know people were just really enjoying the content, so I hope we'll be able to have you come back sometime.
Sounds good.
All right. Thanks, everyone.